Yes, good morning, friends. We have been so far discussing about how to control an airplane in a longitudinal mode, that is, how do I deflect the elevator to trim the airplane at different CL, right? And in this regard, we developed one relationship, that is delta E, that is delta E trim or delta E required is delta E naught plus d delta E by dCl trim into CL trim. Further, we know d delta E by dCl trim, which is this one, this is equal to minus dCm by dCl by Cm delta E. What is Cm delta E? Cm delta E is elevator control power, sign is negative, and dCm by dCl is minus static margin. And so I can write this as N naught minus xCg bar by Cm delta E. This is clear because we know dCm by dCl is equal to minus static margin. Minus of static margin is neutral point minus xCg location. So if I put it here, this minus sign goes, so I have got this. So in a simpler form, so I can write delta E trim or required, whatever you use, is equal to delta E naught plus N naught bar minus xCg bar divided by Cm delta E. And you all know when you say bar means it is non-dimensionalized with mean aerodynamic chord. This is not complete. I have to write here CL trim. So what is the message from this relationship we got? If I want to trim an airplane at a particular CL, once I know this and this, I know how much elevator deflection has to be given. Let's say for an aircraft, low speed aircraft. Low speed means, why I'm saying low speed? Assuming that at low speed, this derivative will not change with Mach number. So they remain fairly constant. And this statement is fairly correct. If Mach number is up to 0.6, then all these derivatives remain fairly constant. So I'm considering at low speed. So that means I know that delta E naught, which is minus Cm naught by Cm delta E, that is also constant. Also, we are assuming that if there is a slight change in the CG, okay, we do not attribute that much of change to change Cm naught. We are assuming Cm naught is constant. But one can always find out exact value. Similarly, your N naught bar, which is for a stick fixed case, is also fixed, right? But we have noticed that this N naught bar may vary depending upon whether power on, power off, or popular windmilling, right? Okay? So now think, if I have taken a particular aircraft and if I want to find out what is the delta E required for a cruise, I'm cruising at a particular altitude where density is rho, then what is the CL required? That I find through lift equal to weight. This implies CL equal to 2 W by S by rho V square. Let us say I want to fly at a particular altitude where density is rho and with a particular speed V, then what is the CL required? I know from here CL will be 2 W by S rho V square, and W by S is the wing loading. You all know that. So what is this relation is telling me now? Well, then this becomes my CL trim for that cruise at altitude where density is rho. I will be simply using this CL value here, right? As you have assumed that Cm delta E naught are not changing. What is the next thing I should check? I know that N naught, I have to be very careful. I have to see N naught for power on, power off, windmilling case. Which case it is? When it is cruising, at cruise, which N naught will be relevant for us? It is not power off, it is not windmilling, it is power on case. So I should put this CL trim here, and along with I will pick up the value of N naught power on and find out what is the delta required. Clear? So this will go there, and N naught power on will come here for cruise. But that's not the end of the story. Suppose you want to cruise such that L by D is maximum. Possible? And you know, for that, typically this is a condition when we say the thrust required is minimum. If we revise, remember for a cruise, thrust equal to drag, lift equal to weight. So I can write thrust equal to W by L by D or equal to W by CL by CD. So from here I can make an observation. If I want thrust required minimum, that means this gentleman should be maximum for a given weight, right? So for CL by CD to be maximum, we know that CD I can write as CD naught plus KCL square, and using this relation I can find out the condition for CL by CD maximum, which we have done in our first course, to be CL equal to under root CD naught by K. Now notice this CL and this CL are not same now in general. This is the CL when I am going for thrust required minimum, or this is the CL when L by D is maximum, right? So now how do I get what is the elevator deflection? What I will do, I will again take this CL value, I will plug in here. Whatever this CL is coming for thrust required minimum, this CL for L by D maximum or thrust required minimum, I will plug in here, right? And then next I will check what is the N naught, because it is also a cruise, although it is in a thrust required minimum configuration or CL by CD maximum configuration, so, but it is power on, so N naught again I will be using power on, correct? Next case you see, let's say climb. How did you model climb? If you recall, this is the plane, this is vertical tail, this is the horizontal tail, this is the wing, and say T, this is D, and this is lift. Let the V be in the same direction. This is W. So this is W cos of flight path angle, which is gamma. Right? So how did you form the equation? We said T minus D minus W sine gamma equal to 0, because we are talking about steady climb. We have done all this thing in your first course. You are advised to go through that. I'll be just glancing through it because it has a relevance. And then here L equal to W cos gamma. So message is, if I want to make a rectilinear flight along this direction, I should ensure that there is no force perpendicular to this velocity vector. If there is a net force perpendicular to the velocity direction, then it will take a curved path. So we must ensure that if you are flying like this, steady climb in a rectilinear path, then I must ensure this lift force should be balanced by the component of weight W cos gamma. So from here, CL I find as W by half rho V square S into cos gamma. And you could see that now if I am climbing, the CL climb is less than CL cruise, right? And that is exactly why you say induced drag during cruise is more than induced drag during climb. What is the delta required? Again, I ask this question. So I will now I'll estimate this CL value depending upon what is the value of gamma. Am I climbing at 15 degree or 30 degrees? Depending upon that, I know the CL value, and this CL value I now put to CL trim And next question of N naught, okay, this is climbing means the power is on, so I should take N naught power on in this case. Correct? So what is the change? Change is only I need to find out the CL for the climb, which is equal to W by half rho V square S into cos gamma. Depending upon what is the gamma, what is the flight path angle, the CL value also will change. CL for climb will change, right? And that value I put here. I check what is N naught. It is climbing, that means thrust is on, the power is on. So I'll be using N naught corresponding to power on. Okay. At this point, you should remember that we have already proved that if this is N naught power off, most stable case, this is N naught on, and this is power on, and this is propeller windmilling. Correct? You are imagining from this reference, and this graph, this variation is typically correct for a nose-mounted propeller-driven engine or an engine. Nose-mounted, that means that engine is, the thrust line or thrust is ahead of CG. The engine is ahead of CG. Okay. Now, the story again doesn't end here. When you are in the operation, let's see what are the things you do, what the pilot would like to do. If I take the climb case, we have seen T minus D minus W sine gamma equal to 0. So I can write T minus D by W is equal to sine gamma, or TV minus dV by W is equal to V sine gamma. We have already done all these things. So what is V sine gamma? If this is V, this is V, V sine gamma is this component. So this is rate of climb. Okay? This is rate of climb. And what is TV? Is the power available. Power available. And this is the power required. And this is the weight. So I know how rate of climb changes with the excess power, that is difference between power available and power required for a steady climb. This is for a steady climb, no acceleration is there. Now, from pilot point of view, if you see, if I write power and V, we know that power required graph will follow something like this. And let's say power available for a particular type of engine, propeller driven, let's say remain almost constant with speed. Wherever this excess power is maximum, this is the excess power maximum. Because you know this is power required, this is power available. So this is the excess power, and then it starts increasing, goes to maximum, then start reducing. So there is a corresponding V, let's say V star, which corresponds to rate of climb maximum. Because I know excess power and this is rate of climb, they are related. Okay? V sine gamma is rate of climb, so they are related. So wherever excess power is maximum, rate of climb also will be maximum. Now suppose the pilot wants to fly at a particular speed where rate of climb is maximum. How is he going to trim the airplane? How much delta he is going to deflect? So you know this is the V. From this chart you know what is the V the pilot should fly. So from that V, pilot should find out CL using the climb equation. And that CL, so this is V star, he finds CL from climb. And that CL, he has to use it here. Okay? That will give him the delta required to fly at a speed for which rate of climb is maximum. Again, he will be using N naught bar, which is for power on. Right? These are, pilot will not compute all these things. The designer, you have to see that these solutions are available. Pilot will go on handling elevator and thrust, etc. together. But if you don't have a solution in the design, then pilot won't be able to get those things through iteration, right? Okay, so these are very important for the understanding for a designer, what you are doing, what are the solution available, what sort of bandwidth you have given for the airplane, right? We have been discussing on the cruise, climb, you know. Now, landing also same story. Same, you have to find out what is the CL and then trim the airplane based on delta equal to delta E naught, delta equal to delta E naught plus N naught bar minus XCG bar by Cm delta E into CL trim. See the landing. During landing, what is happening? Again, the velocity vector is like this, and you want to follow this path. This is the weight, this is the lift, this is the W cos gamma. So CL will be again W cos gamma by half rho V square S. This is fine. So what we will do, you can find out the CL by taking the weight. What weight should I take? When I am landing, this weight is not equal to takeoff weight, isn't it? Because some amount of fuel is consumed. So this weight will be different. So this weight will be less than W takeoff, whatever, when you're computing CL, right? And you have particular speed, so you know what is the CL value. That CL, again, we will be putting here for CL trim. But then, as we have made it a habit, we should check what N naught should I put. In this case, when I'm landing, then we have three cases: power on, power off, and power, that is windmilling. Which one should I pick? Generally, when I'm landing like this, ideally, the power should be 0, because why do you want unnecessary power? But that's not the case for all safety arrangements. So the propellers are generally put in a windmilling condition. That is, when it's moving, it is also rotating because of windmilling effect. And sometimes it is the pilot will set 10% of the power, 10-20% power. But we are thinking of a case where it's a windmilling. So, and we know that N naught for windmilling is in between. This is N naught power off. This is N naught windmilling. And this is, of course, N naught power on. This is typically for a nose-mounted engine. So now, when I'm landing, this N naught should be N naught corresponding to N naught windmilling, because it's not full power on nor it is power off. Okay? And then you will find what is delta E required. Correct? It is as simple as that. But see, there is a catch. This is fine. But when you are landing, what is happening? Let's see. In flight, in cruise, you are flying in air, and you have air and air all through. But when you are coming for landing, what is happening, you see? When you are coming for landing, at some distance, see, there is something called ground effect that we have talked about in our first course. What happens if this is the wing of the airplane? When I'm landing like this, there's a high pressure at the bottom, low pressure at the top, so there will be vortices that come out from this, and they'll be hitting the ground, and there's a reflection, right? And that is typically characterized through ground effect modeling. But for us, what happens? Because of ground effect, primarily one of the important things that happen is downwash reduces. So because of ground effect, the downwash reduces, and what is the effect of that? Let us see. Remember, when we were modeling in free air or free space, were far away from the ground, we said alpha tail is what about alpha FRL, fuselage reference line, plus IT, if I put IT, some setting angle, you can check earlier note, IT plus IT, but minus epsilon. Because of wing tip vortices, there will be a downwash component, and we have seen if this is the free stream V, then the local V at the tail becomes V prime, is tilted downward, and this is the downwash angle. That means what is the message from flight mechanics point of view? The effective angle of attack at tail because of downwash is reduced from the free stream angle of attack. That is the only message. If the downwash was 0, then whatever angle of attack is seen by the wing, same angle of attack would be seen by the tail if there are no tail setting angles, right? Now what is happening? It is you have put the elevator to counter the moment which is coming because of alpha at the tail. Because alpha at tail will give a moment like this down, so you have put an elevator up, so you are balancing it. But what happens as we come near to the ground, maybe within the one span length of the aircraft, this downwash generally reduces and approximately it becomes half. So that means what? The airplane which was streamed earlier, now as it comes close to the ground, suddenly the tail angle of attack, alpha tail, increases because downwash has reduced. If the tail angle of attack suddenly increases, what will happen? It will give a nose down moment like this. So if you want to really land safely, then you have to ensure that this sudden increase in the nose down moment is also corrected by putting elevator up. Otherwise, it will just hit the ground. So this is where, while during landing, you need to have additional care and keeping the delta E or elevator deflection, additional deflection reserve, okay? Only to be used during landing, extra amount, right? How do I do that? How do I solve that? We know because of downwash reduced by half, the change in the tail angle of attack is, it will be CL wing by pi aspect ratio. Because you know epsilon is 2CL wing by pi aspect ratio. We are taking E to be 1, Ostwald efficiency to be 1. So this is this. So this much change in the angle of attack. That means angle of attack of the tail will change by this much amount, right? Because earlier it was twice of this, which was subtracted from tail angle of attack. Now this value itself has become half. So now effectively tail angle of attack has increased, which will give a nose down moment, right? So how do I find out delta E? We know that definition of tau, which is d alpha t by d delta E. That means per unit change in elevator deflection, how much alpha t gets changed. So I can write tau into delta delta E plus CLW by pi aspect ratio should be equal to 0. That means whatever additional increase in angle of attack is there at the tail to be compensated by changing the alpha t through delta E deflection using tau. So from here I get delta delta E equal to minus CLW by tau pi aspect ratio. That means this much of elevator deflection should be kept in reserve, meaning thereby, suppose delta E max is plus minus 15 degrees. What do you have to do? You find out what is this delta delta E required for landing. If it is 3 degrees, suppose 3 degrees this is, suppose, then that means for you to operate in the flight will be maximum of 12 degrees. Because anyway, these 3 degrees you have to keep reserve. Clear? Let's see an example, then you will get better idea. Let's take an example. For a typical airplane, let's say tau is 0.5, CL max, let's say is 1.5, and aspect ratio is 5. So essentially I'm talking about low aspect ratio wing. You could see that if aspect ratio is large, this value will be less, right? So effect will not be, delta required will not be very large. But if aspect ratio is small, as for a high speed airplane, this delta will be pretty high. I repeat, you could see here, this delta E is inversely proportional to the aspect ratio. So if aspect ratio is more, then delta E required will be less, right? We have taken a aspect ratio 5 because typically this phenomena will be for a high speed airplane, what's called recognizable, right? So if I now put delta E, this is equal to minus CL minus 1.5 by pi, let's say tau is 0.5, pi is 3.14 and aspect ratio is 5. So typically this value, if you calculate, it will come down to 10.9 degree, because this will be in radian, this will be in radian, and then multiply 57.3, you will get in degrees, 10.9 degrees. What is the message? Message is, if your delta U max limit is, let's say, plus minus 25 degree, then please remember that 25 minus 10.9, let's say 11, that is 14 degree, is only available for you to trim in free air while landing. Because you know, as I come to land, right, I need suddenly additional of an 11 degree up. So this is minus sign, 11 degree up. So if that time, if I have trimmed this whole airplane at 25 degree, and for landing, if I come for landing and trimmed the airplane at 25 degree, the moment I come close to the ground, it will demand another 11 degree to be taken up. But the moment I put 11 degree over 25 degree, the elevator will not work because it will stall. So what is the message? You find out what is the delta A required. So whenever you are trimming before you come down to landing, make sure from your maximum elevator deflection allowable, this much of angle is left reserved, and you land then only. Okay? That is how you should plan your maneuver. And this is strictly true for very, very significant for lower aspect ratio aircraft, that is high speed airplane. Okay?